Hey folks, my name is Nathan Johnston. Welcome to lecture 23 of Advanced Linear Algebra. Today we're going to look at something called the adjoint of a linear transformation. And the idea behind this is, well, throughout this course we've looked at lots of ways of generalizing properties and operations on matrices to linear transformations. But one thing that we haven't looked at yet is the transpose of a matrix. How do you generalize the transpose of a matrix to linear transformations? And really, what makes the transpose of a matrix interesting in the first place, right? Remember, the transpose, it's this operation on matrices where you reflect it across its main diagonal. In other words, you interchange the rows and columns of that matrix. It feels like a sort of arbitrary operation. So why is it important? Well, it's important because it's the matrix version of the adjoint of a linear transformation. So let's look at this. The adjoint of a linear transformation, what is it? Well, suppose that you've got some inner product spaces, because we're going to see that we need an inner product to work with. And then you've got some linear transformation between them. We say that the adjoint of that linear transformation, and we denote it with a little star like this, T star is the adjoint of the linear transformation. Notice that it goes back the other way. So if T is going from V to W, then T star is going from W to V. And for matrices, you can sort of think of this as, like, remember the transpose, it sort of interchanges the input and output dimensions, right? It turns an M by N matrix into an N by M matrix, okay? So same things here is happening for linear transformations. Input and output spaces are being swapped. And what is the adjoint? How do we define it? Where does it come from? Well, what it is it's the linear transformation that satisfies this funky little property here. What's happening here is, you can think of this as, if this equality here is true, then you can sort of move T from one side over to the other side of the inner product, except you're not moving T, it's sort of transforming into T star when you move it, okay? So adjoints, you can think of them as coming in pairs, right? T acts on one half of the inner product in one way, and T star acts equivalently on the other half, but produces the same resulting number if you do that. Okay, so there's sort of pairs of linear transformations that act on opposite sides of an inner product. Okay, so let's really try to convince ourselves that, first off, the adjoint of a matrix really is its transpose. Okay, that was the motivation here, so let's show that it actually is true. In other words, what I want to show is that, instead of having a linear transformation here, if I just have, like matrix multiplication, then AVW really just equals V A transpose W, okay? That's what we want to show here. So in other words, we're thinking of the matrix as a linear transformation that sends n-dimensional vectors to m-dimensional vectors. All right, and the way we're going to do this is just plug everything into the definition of everything, okay? We're going to use the standard inner product, we're going to use the dot product, and see that this is what we get, okay? So again, we want to show that AV dotted with W equals V dotted with A transpose W, okay? The way we're going to do that, use the definition of the dot product and use definition of matrix multiplication. So over here, I'm first computing AV, okay? So this is a matrix multiplication, and it's kind of ugly, but if you just use the definition of matrix multiplication, this is what you get, right? This is the first row of A dotted with V. This is the second row of A dotted with V, all the way down to the mth row of A dotted with V. And then we're dotting that whole big ugly vector with W. Okay. Next up, I'm just going to write things out. I'm going to do that dot product, right? So that gets me, that turns all these single sums into a double sum, because now we've got this times W1 plus this sum times W2, and so on. So now we've got another sum going on the outside. That's just from the definition of the dot product. And I'm just going to move things around a little bit, okay? Here I've got two sums. Well, I can swap the order of the sums. So now instead of summing over I and then instead of summing over J on the inside and then summing over I on the outside, I'm going to flip it around. So I sum over I on the inside and J on the outside. And also, I'm just going to swap the order of the V's and the W's. Okay, so that's just operations on real numbers. Nothing weird going on there. All right, and now I'm going to stare really, really hard at this double sum over on the right here, and notice that, hey, I can rewrite that sort of in a similar way to what I had up above, except now I'm going to write it as a dot product of a vector with these entries with a vector with these entries. Okay, so this time I'm going to collect all of the V's into one vector, and then all of these sums over I into another vector. Okay, so this is just also a dot product of vectors down here. Okay. And then last but not least, we just stare really hard at this, right? Proof by eyeballs. And we notice that, hey, this, well, that's V. And this over here, well, this is a little bit harder to see, but this exactly is A transpose times W, right? I mean, the fact that it's times W maybe isn't too hard to see here, but the fact that it's A transpose times W, it just comes from, I mean, normally you would have your inner dimensions matching here. Like if it was just A times W, which wouldn't make sense because the dimensions don't match up, but if it was, you would have an I on the inner subscripts matching up. But it's A transpose, which swaps the order of the subscripts, okay? All right, so you get V dotted with A transpose W. So yeah, I mean, that means exactly what we wanted it to mean. That means the adjoint of A, by staring at these two things here, the adjoint of A really is just the transpose of A. Okay, and what that means is that, well, you can move A to the other half of the dot product as long as you remember to take its transpose when you do that, when you take its adjoint. Okay. Similarly, if we're working with complex matrices, something almost identical happens. What happens is the adjoint of a complex matrix is its conjugate transpose A star, right? Remember, conjugate transpose, this means you transpose the matrix A and take the complex conjugate of every entry in the matrix, okay? And the way you prove this is just very similar to what we did up here, so I'm not going to go through it again. All right, and this is actually why the conjugate transpose is important in the first place. This is why we introduced this operation on matrices, because it has this desirable property that, well, to move a matrix from one half of the complex dot product over to the other half, you have to take its conjugate transpose. You take its adjoint. All right, now let's start proving things about the adjoint. Let's see that it has nice properties. And the first thing that we want to do is I want to clear up a little bit of confusion. We've been talking about the adjoint of a matrix or linear transformation, but I mean, how do we know? Okay, so there are a bunch of questions. How do we know that there really is the adjoint? Maybe there's a whole bunch of linear transformations that I could put over in this slot on the right here to make it work. So maybe adjoints aren't unique. How do I know that they are unique? And how do I know that an adjoint exists, right? How do I know that, hey, if I've got some linear transformation over here, how do I know that I can find any linear transformation to fit in that slot? So how do I know that they exist in the first place? Well, let's clear up these questions. And furthermore, I guess, I mean, in arbitrary vector spaces, how could you compute them, even if they do exist and even if they are unique? Okay, so this theorem answers all these questions. All right, so same setup. Suppose you got finite dimensional inner product spaces. We actually are going to need finite dimensional here. The definition works in any inner product spaces. We're going to want finite dimensional for this theorem, though. All right, and then again, suppose you've got some linear transformation between them, and then here's what the theorem says. It says there exists a there exists an adjoint. That adjoint is unique. And furthermore, it tells you how to compute it. So the way that you compute it is you pick any old orthonormal bases B and C of the input and output spaces. And then here's what you do, okay? You can compute it in terms of standard matrices. The standard matrix of the adjoint is equal to the conjugate transpose of the original standard matrix, right? So you compute the standard matrix of T itself, then you take its conjugate transpose, and boom, you've got the standard matrix of the linear transformation that you want, of the adjoint. All right, so let's see how we prove all of this junk here, okay? Where does all of this come from? And the first thing that we're going to do is we're going to prove uniqueness. And actually, at the same time as we're proving uniqueness, we'll prove this formula for the standard matrix of the adjoint linear transformation. So for now, we're proving uniqueness. So we're just going to assume that T star exists. We're not going to worry about existence yet. We'll prove that later. All right, so if T star exists, we want to show that there's not like another T star out there. We want to show that there's only one of them. There's only one adjoint. The way we're going to do that is we're going to start off by computing this quantity T of V inner product with W in two different ways. The first way that we're going to do it is we're going to take T of V inner product with W and we're going to say, well, this is nice. I've got a theorem from last week that says every inner product looks like the dot product, right? As long as you represent things in terms of some orthonormal basis, which I've got here, right? C is an orthonormal basis. So this is true just via a theorem from last week, okay? Inner products look like the dot product. But now I can also break apart this T of V. I have a theorem that says, well, when you've got a linear transformation applied to a vector, that's standard matrix times coordinate vector. That was one of our even earlier theorems from this course, okay? And that does not rely on orthonormality. That just requires these to be bases. All right, now what I got is some sort of ugly, like you got a matrix times a vector dotted with just another vector, okay? And now I'm just going to use properties of, the dot product. You can rewrite this as whenever you have a vector dotted with a vector, you can think of that, if you think of everything as columns vectors, then this is just the star of this, right? It's the conjugate transpose of this column vector, so it's turning into a row vector times this column vector, right? You know, v dotted with w, well, that's the same as v star times w. So that's all we're doing here, okay? And when you take the star of this, it swaps the order of multiplication. All right, so that's one way we were going to compute this quantity, t of v with w. Now I'm going to compute it in a different way. I'm going to get something different, okay? Now, so the other way that I'm going to compute it is I'm going to first use sort of the defining property of adjoints, okay? And that says, well, I can move this t over to the other side of the inner product as long as I turn it into a t star. Okay, but then from here, I'm going to run through the exact same argument that I went through up here. So the first thing I'm going to do is I'm going to represent things as coordinate vectors and say, hey, B is an orthonormal basis. So I can use that theorem from last week that says, hey, inner product looks like the dot product. Okay, next, I'm going to split this up. I've got linear transformation applied to vector and then coordinate vector of the whole thing. Again, theorem from a couple weeks ago says I can split that up into standard matrix times coordinate vector. And then last but not least, again, I have dot product of two vectors, write that as star of this times this. Okay, so that's all I'm doing over here, rewriting the dot product in a different way. Okay, and now I just look at this really, really hard, and I ask myself, what do I have? Well, I have two different things must be equal to each other if I trace all these equalities through, right? This equals this, which equals this, which equals this. So these two things on the right-hand side have to equal each other. So that's all I've written down there. They have to equal each other no matter what v and w I choose from their respective vector spaces. Well, what's that tell us? Well, I mean, I've got the same VB star on the left, and I've got WC on the right. And it is a fact about matrices, this is just an exercise that you can prove on your own, that if you have matrices with the property that multiplication on the left and right by arbitrary vectors always gives you the same number, right? That's what's happening here. I've got two matrices, this matrix, and they're being multiplied on the left and the right by the same vectors. I always get the same number. Well, they have to be the same matrix. The only way that this can hold is if this matrix on the middle here is the same as this matrix on the middle. All right, so that tells us that, yeah, these two matrices are the same. And so first off, that pins down the formula that we wanted from the theorem, right? That pins down this formula here. But furthermore, it actually tells us uniqueness of the adjoint linear transformation as well. Because what's this say? Well, it says if I want to compute the standard matrix of the adjoint, here's how to do it. This is the one and only. You take the standard matrix of the original linear transformation and you compute its conjugate transpose. And then if you just use the fact that every linear transformation has one and only one standard matrix, right? Once you've fixed your bases, B and C, then standard matrices are unique. You find that T star has to be unique as well. There's only one linear transformation with this standard matrix, with this guy over here. All right, so we've got uniqueness, we've got the formula, we still have one more thing to pin down, and that is existence of T star in the first place, existence of the adjoint linear transformation. And the way that we're going to do that is we're just going to sort of follow this argument backwards. I'm going to start off, I'm going to say, okay, well, what happens if I just pick the linear transformation that has this as its standard matrix, okay? So I'm just going to pick the linear transformation that has T star as its standard matrix. And then you can just run the entire argument that we had up above backwards, and we'll see that, yeah, this formula here holds. Because what's going to happen is you're just going to sort of start off with, hey, these two things must be equal, and then you can just sort of trace things towards the middle on both sides, and you'll end up with, oh, well, these two things must be equal as well. And that's what we want. That's the defining property of the adjoint. Okay, so you just run the argument backwards, and you get what you want. All right, so yeah, adjoints exist, they're unique, and we have a formula for actually computing them, okay, in terms of matrices. So let's do a couple examples now, okay? We already did the example of, matrices as linear transformations, but what happens if you have linear transformations on more exotic vector spaces rather than just Rn? Okay, well, let's maybe sort of the next step up is the transpose map, right? Remember, you can think of the transpose map, that's a linear transformation acting on the space of matrices. Let's show that with respect to the Frobenius inner product, the standard inner product, the adjoint of T just is T again, okay? So the transpose map is its own adjoint. Let's see that. All right, so here's the setup. I'm actually going to show this in two different ways. The first way is sort of the by definition sort of way. All right, so if we're working by definition and we want to show that the transpose is its own adjoint, what that means is, well, if I apply the transpose on the left half of the inner product, I can move it over to the right half of the inner product. Right? And because it's its own adjoint, I don't even have to change it. It's still just the transpose over there. All right, so I want to show that the inner product of A transpose B is the same as the inner product of AB transpose for all matrices A and B. The way I do this, again, I'm just going to work from definition, okay? What is this inner product here? Well, it's the Frobenius inner product, so I'm writing down the formula for the Frobenius inner product. Remember, if you have just A and B in this inner product, then it's trace of A star B, right? You would have a star up here on the first entry, okay? But because I've got a transpose here, right, A transpose star, well, the two transposes just cancel each other out, and you're just left with a complex conjugate on every entry of A, but no transpose anymore. Okay, and now I'm just going to rearrange using the properties of the trace. I'm going to rearrange this and write it in a little different way. So the first thing that I'm going to do is I'm going to use cyclic commutativity of the trace. Okay, remember this is the really nice property of the trace that if I have a product of two matrices, I can swap the order of the product. So now I've just got B on the left, a complex conjugate on the right. The next thing that I'm going to do is kind of weird. I'm going to take the transpose of the entire thing on the inside here. Remember, trace of a matrix is the same as the trace of its transpose, because the transpose doesn't change the diagonal entries. Okay, so if I take the transpose of the whole thing on the inside here, what do I get? Well, remember, transposing a product, you swap the order of them and transpose them individually. So this A bar is going to move to the left and become an A star. Now it's a conjugate transpose, it's not just a conjugate. And this B is going to move to the right and become a B transpose. Okay, so that's just from transposing this whole product here. Now you get this expression. Okay, but now that's actually exactly what we wanted, right? This trace over here is the inner product of these two matrices, A and B transpose. Remember that inner product again, the inner product itself puts this star there. Okay, so this is the inner product of A with B transpose. So good, that's what we wanted. So yes, the transpose is its own adjoint. All right, method 2. Another way that we can do this is we can work with standard matrices. So let's see how that works. This method does work no matter what M and N are, but it's a little bit trickier. We've only computed the standard matrix of the transpose in the M equals N equals 2 case. So that's the case that we're going to go through here with standard matrices when both of your input and out, like when you're working with 2 by 2 matrices. All right, so remember this was, an example that we went through a couple weeks ago. Recall if you've got the standard basis of the space of matrices, then your standard matrix of the transpose is this matrix here, okay? So, and maybe it's important to note that remember E, the standard basis of the space of matrices, that is an orthonormal basis, okay? So this is useful here. If you have a non-orthonormal basis, you don't want to do adjoint calculations with it. It doesn't work out. You need an orthonormal one. All right, well, then we just look at this matrix and we say, hey, if I take the conjugate transpose of this matrix, nothing changes, right? It is its own conjugate transpose. This matrix is Hermitian, okay? So T with respect to E star just equals T with respect to E. So yeah, this matrix is its own conjugate transpose, so the linear transformation is its own adjoint by that previous theorem, right? Previous theorem tells you that one way that you can compute adjoints is by taking the conjugate transpose. And here nothing changes when you take the conjugate transpose, so nothing changes when you take the adjoint. So the transpose map, again, that's just another way of seeing that really it is its own adjoint. Okay, and it's going to turn out that situations like this, where a linear transformation is its own adjoint, those are actually really nice linear transformations, right? Because those are linear transformations that you can just move from one side of an inner product to the other freely without even having to change it. So we give them their own name. We say that they're self-adjoint. Okay, and for things to match up here, for all the definitions to mesh together properly, these linear transformations, they only work when you're mapping from a vector space to itself. You can't have a self-adjoint linear transformation that's going to a different vector space. Okay, because adjoints reverse, the vector spaces that you're mapping between. Okay, so it couldn't possibly equal each other otherwise, but if they do equal each other, they're called self-adjoint. All right. So for example, again, if we return to, linear transformations as matrices, and maybe starting off with real matrices, we say a real matrix, it's self-adjoint if and only if it's symmetric, again, okay? And the way that you see this is just think about, well, what's an adjoint of a matrix? Well, the adjoint of a real matrix is just its transpose, okay? Well, if the adjoint equals itself, that just means the transpose equals itself, okay? And we call those matrices symmetric. If we're working instead with complex matrices, well, a complex matrix is self-adjoint if and only if it's Hermitian. In other words, if and only if A star equals A. And again, A star, that's just the adjoint is the conjugate transpose. Okay, so if we want the adjoint to equal itself, well, we need the conjugate transpose to equal itself. And matrices with that property are called Hermitian. And slightly more generally, a linear transformation between arbitrary finite dimensional inner product spaces, it's self-adjoint if and only if its standard matrix is symmetric or Hermitian, depending on what the ground field of your inner product space is. If the ground field is R, then you want your standard matrices to be symmetric. And if your ground field is the complex numbers, then you want your standard matrix to be Hermitian. And you have to be a little bit careful with this statement here. This only works if you're working with respect to some orthonormal basis, okay? All of these theorems that we have that say, hey, you can represent your linear transformation as a standard matrix, well, if there's an inner product in sight anywhere, you actually want to use an orthonormal basis, okay? All of our theorems require orthonormality if there's an inner product in there. Okay. So that'll do it for adjoints for today. So next class, we're going to go on to a slightly new topic. We'll talk about unitary matrices, and I will see you then.